part of our lecture about winter weather, I'd like to talk about different types of snowstorms that can happen that can produce winter precipitation. There's going to be three main types of weather systems that produce snow, and in many ways the simplest one to think about is what we call orographic lifting. Orography is a fancy schmancy word for like mountains. And so orographic lifting is going to be getting snowfall just because you are forcing the air to rise over mountains, regardless of whether there's low pressure, high pressure, troughs, ridges, jet streams, I don't care. Just forcing air to rise over mountains in the winter causes condensation and the formation of precipitation, just like you learned way back when we learned about like the mountain problem. And this is an important part of the story as to like how ski resorts are designed. In general, ski resorts only make money when there is snow, and in general they make money when they don't have to make the snow. So in general, when they are designing a ski resort, they want to figure out what is the prevailing wind in their area, where do the winds tend to come from, and that way they can make the ski resort on the upwind side of the mountain, where the snow will be forming as air is being forced to rise over the mountain. So, I mean, there's a reason. Now, there's more complications as to it than that. I mean, there's a lot of reasons why they build ski resorts where they do, but a major consideration is about trying to get them on the upwind side of the mountain. But really, any kind of weather pattern that forces air up terrain produces precipitation, and in the winter will make it snow. I mean, a lot of our students tend to be from Colorado, maybe even from Denver, and in Denver, the public tends to refer to that phenomenon as upslope snow, and Denver sits at the foot of the Rocky Mountains, and so anytime wind is coming from the east at Denver, whether that's because like there's something with cyclonic rotation to their south, or whether there's something with anticyclonic rotation to their north, who cares? As long as it's causing wind from the east at Denver, it's forcing wind up the mountains, and it can produce enormous amounts of precipitation. And students love to send me things like pictures of, you know, Denver International Airport buried in snow or something like that, and it's cool, okay? It's a good example of a weather phenomenon that is just orographic lifting. A more complicated idea with regard to a type of storm that can produce snow is something you've probably heard of but weren't sure quite what it was. This is lake effect snow. First off, the word is lake effect snow. I remember when I was a student of meteorology, I was shocked to discover it's lake effect snow and not lake fed snow, like the lake is feeding it. And in fact, I hear people say that word lake fed all the time. It's lake effect snow. Lake effect snow is going to happen when cold air blows across a big lake. Now, in the United States, that's principally the Great Lakes in the upper Midwest, but you can get lake effect snow off smaller lakes like Great Salt Lake in Utah. You can get flurries of lake effect snow off of smaller lakes, although in the United States the main ones we're worried about are the Great Lakes. And lake effect snow is going to mainly be an early winter phenomenon, like in October, November, and December, maybe even January, because it's only going to happen during times of year when the lake is warmer than the air that goes over it. The lake warms up all summer, and then in the fall and in the early winter, cold air masses from Canada start coming across it. The cold air masses might be, you know, have temperatures in the 20-degree Fahrenheit range or something like that. And the lake isn't frozen yet. The lake is still pretty warm. I mean, maybe the lake's even as cold as in the 40s or in the 50s or something. But it's pretty cold water, but it is blazing hot compared to the air that's moving over it. And this is going to create a phenomenon that's quite cool called lake effect snow. And it's only going to happen until the lake cools down and freezes over. After that, once the lake is cold, this isn't going to work anymore. But let me actually show you how this is going to work. I'm going to zoom in with my magnifying glass tool here and look at the lake here a little bit more closely. And we're going to picture some cold air, a cold air mass, continental Arctic mass or something like that, coming in from like off of Canada, and it's moving across one of the Great Lakes, Lake Superior or something like that, or Lake Michigan or something. So some cold air is moving across the lake here. And I'm going to try to illustrate this as the wind is going from left to right across your screen here. And I tried to draw like here in that sort of blue box I drew on top of the magnifying glass here. That's supposed to be like a little layer of air or a little column of air as it's moving across the lake here. As it's moving across the ground in like Wisconsin and Minnesota and Canada and so on, it's pretty cold. And so that column of air is pretty cold throughout. But things change quick as that volume of air moves out over that lake. Again, keep in mind, in the early winter, that lake is hot. I mean, don't get me wrong, it's like 50 degrees Fahrenheit, but that's hot compared to the air sliding over the top of it. So very quickly, the air that's right down there by the surface starts warming up just by contact with the lake underneath it. That's conduction. So you start getting air that is warming up at the bottom of this layer, but the air that's even, a few tens of meters up is not touching the lake and is not warming up. And a few hundred meters up, that air is not touching the lake, it is not warming up. So you get a very quick change in the temperature profile of this air, this bitterly cold air that just came off of Canada or whatever, as it moves across the lake. You're heating the bottom of it really, really fast from this lake. And so, as a consequence, if we take a look in that yellow box that I drew on top of that temperature profile right there, we have the situation where the air at the surface is quite warm compared to the air even a few tens of meters or 100 meters above it. Okay, now we learned about temperature profiles in our courses. That's unstable. When that an air parcel near the surface, if it's forced to rise up into that colder air, it's going to be way warmer than above it. And it's going to want to rise, it's going to want to have condensation, it's going to want to have formation of precipitation and so on. That is an unstable situation to have that very warm air, admittedly only in the 40s or 50s or something like that, with bitterly cold air right above it. That's unstable. Air parcels want to rise under those circumstances as soon as they get a chance. And guess what? As soon as they get to the downwind side of the lake, they're going to get their chance. Because as that very unstable air gets to the shoreline on the downwind side of the lake, it's going to start experiencing what we call speed convergence. There's going to be friction again. There wasn't all that much friction over the lake. The winds were not that much affected by friction. But when the winds get to the shore, suddenly there's trees and buildings and power lines and billboards and hills and all the stuff that slows the wind down. Think about when you're in traffic. When the cars are all zipping along the interstate, there's a certain distance they are apart. But when the traffic slows down to go through a construction site, that slowing down brings the cars closer together. The cars converge. That's just an analogy, but that's kind of how speed convergence works. As the flow slows down at the shoreline due to the sudden friction there, there's convergence at the surface. And anytime you've got convergence at the surface, we now know whether we were talking about thunderstorms or the ITCZ or any of a number of different phenomena over the course of the semester. We know that when you have convergence at the surface, you're going to get rising motions. We're having rising motions in air that's unstable. You're effectively getting thunderstorms of snow. In fact, it often is that lake effect snow produces thunder snow. Snow with lightning and thunder. But no matter what, this is an incredibly efficient way to produce heavy, heavy snow. We have made the air very unstable as we dragged it across that very warm lake. And then when it reached the shoreline where there was friction again, we gave it an excuse to have convergence and rising motion and change all of that into water vapor that probably evaporated off the lake into snow. This works best when the winds are blowing the long way across the lake, when the winds have a long fetch. Fetch is a tricky vocabulary word in meteorology that means like how long the winds blow across an open area. If the winds are blowing the short way across Lake Michigan or the short way across Lake Superior, we don't get all that much lake effect snow. But most of the Great Lakes are kind of long and narrow, and if you can get the wind blowing the long way across the Great Lakes, you get a lot of snow. I used to teach at the University, Valparaiso University up in northern Indiana, which is right at the tip of Lake Michigan. And every now and then in the winter, the meteorology program was in the basement of a building, and you'd come in the morning, park your car, go down in the basement. The wind would be just right that you'd get lake effect snow. You come up for lunch, and there's a foot of snow on the ground. You can get crazy amounts of snow when the wind is just downwind and you have a long fetch across the lakes. Lake effect snow only happens, therefore, on the downwind side of lakes. As the wind blows across the lake, on the downwind side is where you're going to see lake effect snow. And lake effect snow can really add up. I mean, if you just look at a climatology of average snowfall, you can see that plenty of places that are on the downwind side of like the Great Lakes see, in excess of 100 inches of snowfall per year. Just to give you a sense, the average amount of snowfall per year in Omaha is about 30 inches. So, I mean, this is a heck of a lot of snow. Even that little star right there in Indiana, I believe that with the 73, I believe that is Valparaiso. Yeah, I mean, 73 inches of snow, that's more than twice what we get in Omaha. And you can see, like, there is some station there that has 200 inches of snow. Lake effect snow can produce an enormous amount of snow. The other type of snowstorm I want to talk about is the one, I mean, we don't get orographic snow in Omaha, there's no mountains. We don't get lake effect snow in Omaha, you're not going to get lake effect snow off of, Heartland of America Park or something. It's not a long enough fetch. What you get snow from in Omaha are cyclones, just ordinary mid-latitude cyclones, or blizzards, which are just, when I say blizzard, I mean a particular set of conditions inside of the mid-latitude cyclone. Let's be technical about that. A blizzard is a period of at least 3 consecutive hours that have winds of at least 35 miles an hour and falling or blowing snow that is reducing visibility to a quarter mile or less. A blizzard explicitly has to have strong winds. That's what makes it a blizzard. And it has to have snow that is limiting the visibility to, like, what does it say, quarter mile. But it does not require it to be falling. If the snow is just being pushed around, if there's just blowing snow, like snow that was already on the ground being blown, that's okay too. That can be a blizzard too. Strictly speaking, that is a type of blizzard called a ground blizzard. Ground blizzards are the damnedest thing. But they're a very real thing. I remember one year I was in grad school and wanted to drive home for Christmas, but I couldn't get there because there was a ground blizzard. You get outside in your car and you get out on the highway, you could not see an eighth of a mile ahead of you, and you look up through the sunroof of the car and it's blue sky. It was just strong winds blowing the snow around, but you couldn't drive. It was a ground blizzard going on. Most of the time, when people use the word blizzard, they're misusing it. They are not actually experiencing 35 mile an hour wind is a pretty strong sustained wind for 3 hours straight. That much snow that your visibility is limited that much. It's not that common. But snowfall in the form of mid-latitude cyclones are certainly very common. Therefore, it's going to be useful to know things about how mid-latitude cyclones move across the United States in the winter. What are their preferred regions to form, and what are their preferred tracks? There are preferred regions to form. When we learned about cyclogenesis a couple modules ago, we didn't talk about it, but it turns out cyclogenesis doesn't work equally well everywhere on Earth and doesn't work equally well all times of the year at those locations. It turns out there are complicated issues, largely associated with like the shapes of mountain ranges and so on, that make there places where cyclogenesis tends to happen. We tend to form a mid-latitude cyclone, and then the cyclone can move off in a preferred direction or whatever based on like where the jet stream is and so on. So let me show you 3 examples of these sort of common tracks that cyclones will follow, where they'll have formed in a common location and then be carried off by the jet stream in a particular direction. Our first example is the so-called Alberta Clippers. Alberta Clippers are mid-latitude cyclones. They are mid-latitude cyclones that form over the Canadian province of Alberta. That turns out to be, especially in early winter, a preferred place where cyclogenesis happens a lot. And then these so-called Alberta Clippers, are these mid-latitude cyclones, get carried off kind of along the Canadian-US border out towards the Atlantic. The word clipper here refers to like clipper ships, as in they move really fast. And that's one of the defining characteristics of these Alberta Clippers, is that they are very fast. I mean, they'll form over Alberta today, by tomorrow they're over Quebec, and by the next day they're way out to sea. They move pretty fast, but they form pretty often. I mean, maybe 15 of these a month in October, November, and December or something like that. They happen pretty fast and pretty frequently, but they're also pretty dry. I mean, let's face it, there's not a really good source of moist air masses in central Canada to be working with. So each individual Alberta Clipper doesn't really produce all that much winter weather, maybe like an inch of snow as they move through. But if you're going to be getting, say, 15 of these systems coming through over the course of a month, and each one of them is dumping an inch of snow, and you're talking about like the northern tier of the United States and southern Canada, where by that time of year it's cold enough the snow's not melting, this adds up to a lot of snow. And in fact, while each individual Alberta Clipper might not produce all that much snow, over the course of, say, the month of November, we'll have added up to snowpack, right? All of North Dakota, Wisconsin, Minnesota, Ontario will all have been blanketed with snow by the end of the time when all these Alberta Clippers are coming through. Alberta Clippers don't in general affect the weather in Omaha. If we're talking about winter weather in Omaha, where we don't get orographic lifting, we don't have mountains, and we don't have a big lake, so we don't get lake effect snow. Snow in Omaha comes from mid-latitude cyclones. In particular, comes from the kind that we call Four Corners lows, or Colorado lows. They call them four corners lows because they happen at the four corners, that only place in America where four states touch. In this case, it's Arizona, New Mexico, Utah, and Colorado. But again, that's another place that is favored for cyclogenesis. It has to do simply with like the shapes of the mountain ranges and so on. That has to do with production of the factors that went into cyclogenesis. We get a lot of cyclones that form around the four corners and get carried up across the United States, kind of up the Ohio Valley. And that tends to be the kind of weather system that produces snow in Omaha. For that matter, it tends to be the kind of system that produces snow where I live in southern Indiana. But neither Alberta Clippers nor Four Corners lows are really comparable to Noreasters. Noreasters are also a mid-latitude cyclone. They work very much like the kinds of things that we learned about when we learned about mid-latitude cyclones. But they form preferentially in like southeast Texas and Louisiana. Again, it's complicated as to why that's a preferred place to form them. And they track kind of along the U.S. coastline up towards Maine. And Noreasters are very, very wet, because they have no shortage of water vapor to work with. I mean, they can pull warm, moist air masses up over the Gulf of Mexico or off the tropical Atlantic, lift that layer, that warm, moist air up off the ground over a warm front or something, and produce lots and lots of snow. And they're moving across a particularly populous part of the country. When you hear about, oh, they got 20 inches of snow this weekend in Boston, that's a nor'easter. Or the DC is closed down because they got 4 feet of snow, that's a nor'easter. Okay? I hate that name, Noreaster. It's a stupid name. People think that it's because they move northeast, or they think it's because they affect the northeast, and neither of those are right. It has to do with the fact that these storms tend to have strong winds out of the northeast before they come. So if you're like an old Gloucester fisherman back in Massachusetts, I don't know what accent I thought I was doing there, you know that a nor'easter was coming when there were these strong northeast winds. It's a stupid name. Don't get bogged down in the name. But they're another type of storm. Now, nor'easters don't happen all that much, maybe 2-3 times a year, but because they're hitting such populous parts of the country and they have so much water to work with, they definitely make the news. Now, before we go on to the fifth part of the lecture, which is just about safety type stuff, let's answer a couple quick questions about these winter storms. Question 11. Lake effect snow happens in the blank, early or late winter, when lakes are much blank, colder or warmer than the air masses that pass over them. Pick the right combination to answer that question before we go on to number 12.